Students, welcome to Quest Head of Physics. Today we are going to do one more application of the dipole. In previous videos, we have learnt about how to find the electric field intensity on axial line and as well as the equatorial line of a dipole. In this class, we are going to learn the potential due to a dipole at any point. Listen the words carefully, students. In this class, we are going to derive an expression for the potential due to a dipole. The two potential at any point due to the dipole, and it is represented here, students. Let's take a set of charges. One is the negative q and second is the positive, the two being separated by certain distance. Here we have to find out the potential at point P. To find out the potential, let's imagine that we just kept a unit, positive charge here. This students. Here, this charge is at a distance of r from the center of the dipole. Let's say this distance is a, and here is a. Okay, students. Potential at point, we have to find out from this charge to this charge. That's why I'm connecting the two centers. Okay, here students. Okay, students. In the same way, from here to here, we have to find out the distance. Okay, students, let's say this distance is R2 and it is R. Okay, students, this is the distance R1 and it is R2. And if you watch it clearly, you will understand that R2 and R1 have different magnitudes, isn't it? If you watch it, R2 is longer than R1, and we have to find out the potential at this point with respect to this distance. So we are going with a little geometry of this distance. Here, to understand this, first you have to learn the basics in what's that angles. For example, you say the two lines are very close to each other, and it is the angle between the two. If you drop any normal from any line, this length, this is the length, might be equal to this one. It is possible for the smaller angles. Here, if the angle is large, then if you drop a normal from here, then what happens? This will intersect this point here. In this case, you cannot say this length is equal to this one. Okay, students, for the smaller angles only, this thing can be possible. Just remember this. Here, we have to use the same thing to find out the potential at point P, which is situated at a distance of r from the center of the dipole. Okay, students, to find the distance between what's that the charges to the point P, I'm doing a little geometry here. I'm connecting this point from here, and similarly I'm extending this. I'm following the same principle what I did before. Okay, students, and I'm connecting this point. Let's make it clear, students. Okay. You say I'm making it somewhat shorter. To understand the things very easily, I'm making some arrangements. Okay, I'm trying to draw the similar triangles here. First students, if watch it carefully, this distance is it and it is it. Okay students, then I have to find this distance and as well as this distance students. See, this is higher than this. Okay students, let's say it is a theta and it is theta. So students, I said it is A and automatically this length is also A. Okay students, we watch this diagram carefully, we can write the R2 and as well as R1 with respect to R students. Okay, getting me students. Here R1 has to be written in terms of R. I need this distance students. If was this, you will get a triangle. Let's say it's A and we have a chart plus Q here. Say B and it's C. If you take and it is D. And it is, say it is E. Here if you take this triangle BCD, if you take the triangle BCD, it is A and it is A cos theta students. If it is A and it is A cos theta, and you know that cos theta is equal to K adjacent to hypotenuse. Okay students, adjacent to hypotenuse. This is similarly this length. Okay students, is equal to A cos theta. Getting me students? Then R1 can be written as R minus A cos theta and R2. You need this one. And this length is equal to this. R2 is equal to R plus A cos theta. I hope you understood students. It is the key point to understanding this topic students. R1 is equal to R minus A cos theta. R2 is equal to R plus A cos theta. Okay students, let's say we have to find out the potential and you know that potential can be had as V is equal to Q by 4 pi epsilon naught into R. Okay students, we are finding the potential with respect to this positive charge. Then we can write it is V1 is equal to Q by 4 pi epsilon naught into R1. Okay students, and it can also be written as V1 is equal to Q by 4 pi epsilon naught and R1. R1 is equal to R minus A cos theta. Similarly, we have to write the potential due to the negative charge, that is minus Q by 4 pi epsilon naught. In the place of R, we have to put R2, that is R plus A cos theta. Okay, if you take 1 by 4 pi epsilon naught is K, then you can write V1 is equal to KQ by R minus A cos theta and V2 is equal to minus KQ by 4 pi epsilon naught into R plus A cos theta. Okay students, we have to find out the potential at this point. That means the sum of the two potentials V1 and V2. The net potential at P is V is equal to V1 plus V2. Then we can write is what? Q by 4 pi K cube by R minus A cos theta minus K cube by R minus plus it is A cos theta. Here it can also be written as KQ of 1 by R minus A cos theta minus 1 by R plus A cos theta. This students. Further it can be written as KQ of R plus A cos theta minus of R minus A cos theta by R minus A cos theta R plus A cos theta. It is in the form of A squared minus B squared. R squared minus A squared cos squared theta. Okay, further it can be written as K cube of R plus A cos theta minus R plus A cos theta by R squared minus A squared cos squared theta. Okay, students, it can be written as, here R get cancelled, K cube of A squared, A cos theta plus A cos theta, 2A cos theta by R squared minus A squared cos squared theta. Yes, students. Okay, students. Here we know that Q into 2A. Q multiplied with the 2A is equal to what? P naught. Then it can be written as K into P cos theta upon R squared minus A squared cos squared theta. It is the potential at P due to a dipole, students. Okay, students. Here, and we go with the special cases, students. Let's say we are going with the special case. We know that V is equal to potential is Kp cos theta by R squared minus A squared cos squared theta. Well, students, let theta is equal to 0. And as you know that cos 0 is equal to 1, then potential V is equal to what you get? Kp into 1 by R squared minus A squared. Okay, students. In the same way, if you take theta is equal to 90 degree, then what you get? You know this way. V is equal to cos 90, 0. That means potential is 0. It means that when the inclination is somewhat, then we will get the potential at various points. If the inclination is 90 degree, that means what? These are perpendicular. This is to that point here. It's fixed. Then theta is equal to 90. As you know that cos 90 is equal to 0. Then we get the potential is equal to 0. I hope you understood this topic very well, students. Okay, if you like, subscribe my channel and forward your friends. Thank you for watching my videos.